Hi, I'm Hiromu Taketsugu from Toyota Technological Institute, Japan. In this video, I will present my paper, Physical Plausibility-aware Trajectory Prediction via Locomotion Embodiment. This work was done in collaboration with Takeru Oba and Takahiro Maeda from TTIJ, Professor Shohei Nobuhara from Kyoto Institute of Technology, and Professor Norimichi Ukita from TTIJ. Let's start with an introduction to human trajectory prediction, HTP. Given the past observation of a human, we want to predict the future trajectory of the target. To improve the HTP performance, recent works incorporate human poses. However, even with pose input, they still produce physically implausible predictions as shown here. So, we asked, how can we make these predictions more physically plausible? In response, we introduce our key idea, locomotion embodiment. Inspired by locomotion generation methods like trace and pace, we use a physics simulator where the agent tries to follow the given future trajectory. Here, we can take advantage of an interesting property derived from physics simulation. If the predicted trajectory is not physically plausible, the agent simply cannot follow it. While such failures are undesirable in locomotion generation, we can use them as a signal to evaluate the plausibility of the given future trajectory. By incorporating this plausibility score into HTP network training, we can promote physical plausibility-aware trajectory prediction. Here, given the same humanoid state and the corresponding future trajectories like this, a future trajectory with higher plausibility score is expected to be closer to the ground truth. Based on this idea, we evaluate trajectories by their plausibility scores. However, we cannot directly feedback the plausibility scores to the trajectory predictor, since a physics simulator is usually not differentiable. So we start with training a loco-val function, a module that estimates plausibility scores of locomotion generation. This loco-val function acts as a differentiable surrogate model of the pre-trained locomotion generator built upon an indifferentiable physics simulator. Then, we use this learned loco-val function in two ways. First, during training the HTP network, we evaluate the plausibility scores of prediction by our embodiment locomotion loss, M-loco loss for short. By incorporating this M-loco loss as a regularization term in addition to loss with the ground truth, we promote more plausible predictions. Additionally, we propose a second use of the learned loco-val function, a test time filtering method called loco-val filtering. By using the plausibility scores estimated by the loco-val function, we filter out implausible predictions at inference. Now, let's move on to the experimental results. Here, I'll present our findings on the JTA dataset. We also present results on several other datasets in the paper, so please check out the full paper via the link in the video description. This figure shows prediction errors when predicting 5 candidate trajectories. The baseline method, social transmotion, achieved an ADE of 1.86. Using the same architecture with our M-loco loss, the error dropped to 1.68. With the additional loco-val filtering at inference time, it further decreased to 1.65. It demonstrates that M-loco loss and loco-val filtering effectively improve HTP performance. Here is a qualitative comparison. The baseline predictions on the left are diverse, but they tend to be implausible and inaccurate. In contrast, our predictions on the right are physically plausible, maintain diversity, and are closer to the ground truth. Next, we show the estimated plausibility scores used for loco-val filtering. In this visualization, darker purple indicates lower scores, while brighter yellow represents higher plausibility. As you can see, predictions that are closer to the ground truth tend to receive higher scores, demonstrating that our method can reasonably evaluate the plausibility of trajectories. To summarize key takeaways, we propose a novel framework, locomotion embodiment, to promote more physically plausible human trajectory prediction. As a result, our M-loco loss and loco-val filter can enhance HTP performance in terms of plausibility, diversity, and accuracy. If you're interested, please check out our project page. Just scan this QR code. Thank you for watching.